So we will start. Thank you for being here. Be welcome to Playa del Carmen. And this school is organized by Carnegie Mellon University and the Advanced Institute of Cosmology in Mexico. In the past, we have been organizing a few schools. This is the sixth school now organized together with CMU. Well, we welcome everyone, and we hope we will have an interesting school. And for that, we have planned some discussions at the end of the day. And we hope all of you have many questions in cosmology, and we have the experts here, and we thank them to be here. And saying that, I just pass the microphone to the chair, Rupert Croft, who is also an organizer.
All right, thanks, Jorge. So I'm Rupert Croft from Carnegie Mellon University. I'm going to chair this first session. And so Raphael is the speaker. He's asked if you have questions during the talk, please interrupt him. We'll pass the microphone around, and then we'll have a time for questions at the end of his talk as well. So Raphael is one of our first lecturers. He's going to give 3 one-hour lectures on the cosmic microwave background. And Raphael's from the University of Texas, and this is his first lecture on this topic. Thank you.
I have one.
Oh, sorry.
Okay, thanks. Well, first of all, thanks to the organizers for bringing us to this beautiful place. And also thanks for asking me to talk about the cosmic microwave background. It's very nice physics, and it's one of our main building blocks in trying to understand the early universe, so I'm happy to talk about it. And as Rupert said, if there's questions along the way during my talk, you can ask me right away, because it probably means that there's something unclear about what I said, and it might be better if people can follow along in real time. And then there's also questions in the afternoon. Okay, so the outline for the 3 lectures roughly is this. So today I'll spend some time trying to explain why people actually expected there to be a cosmic microwave background. And I'll say something about the early CMB measurements and just the spectrum of the cosmic microwave background. And in the second lecture, I'll talk about the CMB anisotropies, the plots that everyone is looking at most of the time. And then it's basically just the basic formalism and the physics behind the CMB anisotropies. And in the third lecture, I wanted to say a little bit about how the cosmological parameters are actually derived from the cosmic microwave background. That means I'll say a little bit about likelihoods and how they're actually made, which means that we'll talk a little bit about real-world issues like masks and foregrounds, etc. And then I'll say a little bit about how the parameters are derived using Markov chain Monte Carlos, and then discuss recent results. So that's the outline in any case. We'll see how it goes. And then for the lecture 1, I thought I wasn't sure exactly who the audience is, how far along everyone is, and so I wanted to give a brief review of general relativity, just so everyone can follow along and everyone knows the conventions and that I'm using. Then I'll spend some time on the work that led to the prediction of the cosmic microwave background. I'll talk about the discovery and say a few words about the spectrum. And so the audience is very mixed from what I understand. So there's experts in the field, and then there's also students. So it's a little bit challenging to make a talk. I was trying to make a talk that everyone can follow along, all the students can follow along, and also a talk that doesn't bore the experts too much. Probably that means in the end that no one can follow along, and I'm still boring the experts, but we'll see how it goes. So let's start with a brief introduction to general relativity. So here I'm just showing you a little comic that everyone's seen many times, I think, and the original reference. So this is the title from Einstein's 1915 paper, which is why we celebrated 100 years of general relativity last year. And what this little thing is supposed to illustrate is the basic ideas of general relativity, namely that gravity, you shouldn't think of it as a force, but gravitational attractions arise because space-time is curved, and the geometry of space-time is determined by the matter distribution. So if you have a matter, some amount of matter, like the sun, for example, it will curve space-time, and the Earth orbits around the sun because of this curvature of space-time, not because of some force, but because of the local curvature it sees. And to make sense of it, this is really the basic idea, and from here you can in principle derive everything, but in practice we'll need to know a little bit about the formulas that go into it, and so we'll need to know how we describe the geometry of space-time. And before we discuss the geometry of space-time, I thought we'll just talk about how to describe the geometry of space. And everyone in general relativity uses Romanian geometry. So this goes back to Riemann in 1854. This was his habilitation, which is something not like the PhD thesis, but something that one had to do before you can become a professor. So this is when he developed Romanian geometry. And the basic ingredient in Romanian geometry is the metric, or the line element. The line element, the idea for physicists essentially is that it gives you a notion of the distance between nearby points. So let's leave it at that. In flat Euclidean space, we know how to do this. So if you have 2 points, a point here and a point here, and you want to know the distance, the s between them, then you know from Pythagoras that the s squared is just the x squared plus the y squared. So this is the line element for flat 2-dimensional space. To make it a little bit more interesting, you can look at a sphere, and then on the sphere you can again ask what's the difference between what's the distance between these nearby points. And in this case it's a little bit more interesting. So you have the length here is just d theta. The length here is sine theta d theta for a given amount of displacement, or in phi. You get further along if you're down near the equator than if you're close to one of the poles. So there's the sine theta. And if you compute the distance now using Pythagoras again, you get that the s squared is d theta squared plus sine squared theta d phi squared. And so this is the line element for a sphere. I mean, this is the distance that inherits from the 3-dimensional space that it's sitting in this case. Now, let's then try to generalize this. This is what Einstein did to a line element for space-time. And in this case, so this is his original notation. Here, mu and u are summed over just in the same way that I and j were summed over earlier. And in this case, the simplest example is just Minkowski space that everyone's familiar with. And you just have the dx squared from the flat 3-dimensional space, and then you have the minus dt squared. So I'm assuming that everyone has seen special relativity, and the minus sign here makes sense. If not, then you really should think of families of observers that are moving with respect to each other at some velocity, and use the fact that the speed of light, which I'm setting to 1 here, is the same in all reference frames, and then this becomes a natural quantity to define. So for cosmology, what we're interested in are somewhat more interesting geometries, and the line elements, then we can think of it as one time slice at a time. So if we're looking, for example, at some initial time, t1, then you might imagine this is actually what our universe is described by to a very good approximation, just flat Euclidean geometry. So the distance between nearby points at a fixed time is just some co-moving distance, the x squared. By the co-moving distance, I really mean the distance between typical galaxies, let's say. So if you want to go from here to here, it's just the x squared plus the y squared again. And then there's something that keeps track of the physical distance between these things. And if you look at it at a later time, the galaxies might have moved apart, and you get a distance that is just a line element that just has a new scale factor here. So you can put that together as a function of time and get a line element like this. And then if you play the movie, you just get the galaxies that are flying apart as described by the scale factor. So I'm assuming most people have seen this metric. More generally, This was for the flat spatial slices. More generally, one might consider other symmetric spaces. So you might consider a three-sphere, or you might consider a hyperbolic space. In this case, the line element looks like this. For k equals 1, you get the sphere. For minus 1, you get the hyperbolic space. And fortunately, we're in the situation where actually the simplest case describes all the data. So our line element, the one we'll be interested in, is flat. But this, in any case, is what people are constraining when they're constraining the curvature. So this means also, if you look at it, this means there's only really the scale factor to encode the geometry of the universe. And in a spatially flat universe, the physical quantities should be independent of its normalization, just because this is just a change of units. So, for example, you can define the ratio of the scale factor at some time t divided by the scale factor at the present time. And I'll call this 1 over 1 plus z, and the z is often called the redshift. We'll see why that is. I haven't yet told you, but this is just a definition. But this is one interesting physical quantity that you can define that doesn't depend on the scale factor, only on ratios. Another quantity is just the fractional rate of change of the scale factor, or the Hubble rate, which will play an important role. So this is just how fast space is expanding at a given time t. Now what we'll need is some equation that governs the dynamics of these objects, and this is where general relativity comes in. So everything I said before is really true in a general metric theory. What I'm saying now is specific to general relativity. So the dynamics of these objects is governed by the Einstein equation. So there's some set of equations that looks like this, where r mu nu is the Ricci curvature, r is the Ricci scalar, which is just a version of the Ricci tensor contracted with the metric. These curvatures look a little bit horrible, so these are the Christoffel symbols, which are constructed from the metric in this way, but what you see is that this is some second order differential equation for the metric, and this is the stress tensor T mu nu. So these look much nicer if you really think about it in terms of differential geometry, but this is usually how they're written in physics. So this is something that follows from the Einstein-Hilbert action. So you can start from this action in principle and derive the equations of motion, and you get the equations that I had on this slide. Now, if you vary this action with respect to the metric. Just as an aside, I wanted to point out briefly that really, so you might ask, well, why do we write down such an action or these equations of motion? Why don't we write down some other equations of motion? And you can show, once you think about it at a somewhat deeper level in quantum field theory, that any theory that contains a massless spin 2 particle at long distances or low energies will be of this form. So this is really a very, very generic low energy effective theory for any theory that contains massless spin 2 particles. And then there are in principle higher order terms. So there's R squareds, there's Riemann squareds, Ricci squareds, there's higher order curvature terms that can appear. There's also higher derivative terms for the matter action, but these are all irrelevant at long distances. So at low energies, and in particular in cosmology, we're really interested in very long distances. So in this case, the leading order piece, the Einstein-Hilbert action, is a very good description. So what does it look like in practice for our simple FRW universe? You can work out the equations. If you haven't done it, you should do it as a homework exercise. There's plenty of time in the afternoons that you shouldn't be spending at the beach, but working these out. Anyway, but so what you find is that the 0,0 component of the Einstein equations just becomes what's known as the Friedmann equation. It's just h squared is 8 pi g over 3 times rho. And maybe at this point I should have still kept the curvature, but I didn't, so there would have been a term that's k over a squared. Then for the ij part of the Einstein equations, so the reason I'm only writing one is because everything I've been doing is rotationally invariant, and so the ij component has to be proportional to delta ij. So there's something multiplying delta ij, and the something that's multiplying delta ij is this equation. You can combine them by taking a time derivative of this one and then adding them, and you get a conservation equation, which is what we'll usually use. So usually the two equations that people use is the Friedmann equation and the conservation equation, but it really just follows from the two equations that you get from Einstein's equations. So if you, this is not a closed system, you have to somehow specify what the pressure is doing as a function of the density, and typically we'll write the pressure as a function of the density in a simple form like this, where P is W times rho, W equals 0, you may recognize as just dust. W is 1/3 is radiation, and you can work out this equation very easily. You get a 1 plus W here, and then you see that the energy density just scales like 1 over A to the 3 times 1 plus W. So this is the solution to this. And then if you want, you can plug this into the Friedmann equation and work out the dependence of the scale factor on time. Typically, we're interested in somewhat in a situation that looks like this. So you have the expansion rate is equal to, and then there's different components here. There might be some matter around, like the baryons or the dark matter. There might be some radiation around that we'll talk about much more in the later part of the talk. And then there might be a cosmological constant or some form of dark energy around. And for matter, we know how it scales. Well, first of all, I said matter is described by P equals 0. P equals 0 really just means that the pressure is small compared to the rest mass. So once you have P equals 0, you know it redshifts like 1 over A cubed. This shouldn't come as a surprise. If you have a bunch of particles in a box and you make the box bigger, then the number of particles stayed the same, but the density went down like 1 over the volume. So this is what you're seeing here. For radiation, we know from thermodynamics that P is equal to 1/3 rho, and if you solve the equations, you'll get that it redshifts like 1 over A to the 4th. And we'll just in a second see where this extra power is coming from. So this is also very intuitive. And then the dark energy may or may not be a cosmological constant. If it is a cosmological constant, then the energy density in it is just a constant, which is where the name comes from. So next, this is something that will come up as we go along, or is something that you should know about to have some intuition about what's going on. If you have particles moving in a general space-time, then their action will look like this. So what they're trying to do, this is their proper time, so they're trying to maximize their proper time. If you vary this action to derive the equations of motion, you find that it leads to the geodesic equation. So they travel along what's the closest to a straight line. And if you work this out, I mean, I gave you the definition of this in the FRW universe. If you work it out, you find that in the FRW universe, the geodesic equation just reduces to this equation. Now, the Christoffel symbols looked a bit like a mess earlier, but in the FRW universe, you can use the symmetries of the problem. So there are really two that you have to compute. Everything else, at least in the flat FRW universe, vanishes. The only two you can write down is you have a gamma 0 ij. This must be proportional to delta ij, and it's just a dot delta ij. The other one that you can have is gamma I 0j, which is a dot over a delta ij, which is the one that's entering here. So a dot over a we define as h. So you just get this equation, and this is easy to solve and tells you that this quantity, dxi by d tau, goes like 1 over a squared. Now, why is this interesting? It's interesting because you can define the momentum of these particles. So this is just the generalization of the momentum, you know, from special relativity to general relativity. And then you see that from the metric, from the spatial part of the metric, you get a factor of a squared. And both of these go like 1 over a squared. So at the end of the day, you are left with 1 over a squared inside the square root. After you take the square root, you see that it redshifts like 1 over a, or scales like 1 over a. So as the universe expands, the particles lose, the momentum goes down. And this is, a different way to write it is if you have a particle that's emitted at some time t and has a momentum p at this time, then if we observe it today at time t0, it's redshifted. So it looks like this. And this also explains why the energy density in radiation went like 1 over a to the fourth. So the 1 over a cubed is coming just from the expansion of the volume, and then there's an extra power of a because the energy in these quanta is redshifted. Okay, so this is the basic kind of review slides I had on general relativity. This is part 1 because eventually we'll have to look at perturbations around this space-time. But I don't know. So if there's any questions about these parts, maybe you can ask now because I'll rely on them later on. Okay, so everyone's familiar with it, it seems, so that's good. So the next part of the talk, what I wanted to do is to say a little bit about why people actually expected there to be a cosmic microwave background. And we'll come to the history a little later, but all this stuff I'm telling you was actually essentially forgotten by the time the CMB was discovered. So the history is a little bit curious. It was it was predicted, but actually it was already observed indirectly before it was predicted. We'll see that also, and then eventually was seen directly. So what were people thinking about when they came across the prediction of the CMB? They were trying to understand what explains the origin of the chemical elements we see around us, and in particular their relative abundances. What you can do is, or what Gamow did in 1946, or at the time, I should say, at the time, the idea was that there's some equilibrium process that generates the chemical elements. How exactly this was supposed to happen wasn't clear, but it was assumed that it was somehow happening in thermal equilibrium. And as Gamow pointed out in 1946, if you extrapolate backwards the equations we just had, then the expansion rate of the universe at the time these elements are supposed to form is actually quite high. So the conditions necessary for rapid nuclear reactions were existing only for a very short time. And so he argues that one should think more carefully about how these elements actually formed, and maybe they didn't form in an equilibrium process. Now, this was the first paper in 46. His graduate student, Alpher, was working on it for his thesis. And then what the idea was, or what Alpher studied, was the idea that the elements formed not in some equilibrium process, but in some fairly rapid process where neutrons are captured by lighter nuclei. So they're built up one by one by capturing neutrons. So the idea is you start with a universe filled of neutrons, and then you build up the elements just by capturing neutrons. They decay, you get some protons, and then the other neutrons get captured on these protons, and you build up all the chemical elements in this way, out to, I guess, uranium in this case. And what one can do is use these equations to derive, you can solve these equations, and then the independent time variable is something like this. And you can determine this by fitting it to the abundance of the heavy elements, is what they were fitting it to. We'll see that that's not really reasonable, but this is what they were doing. They were fitting this kind of quantity, adjusting this quantity to fit the abundance of the heavy elements. Or equivalently, instead of using the integral over the number density, you can use the integral over the energy density, just because it's just related by the mass. Now, this is what the data looked like. So these are supposed, there were no labels, I guess, on this plot, but this is supposed to be the relative abundance of chemical elements as a function of A. So there's some zigzagging going on, but as a whole, you have some exponential decrease, and then it roughly plateaus. And in the equilibrium computations, you would have expected the exponential decrease to continue at higher energy. So this is one of the reasons why they thought they were on the right track, and they could fit this for one particular value of this quantity, let's call it n times t. Now, in the paper, for whatever reason, they got a number that's off by 10 orders of magnitude. If you do the numerics, it just isn't quite right. But Alpher also found the mistake and fixed it in 1948, and then does the same exercise just more carefully and gets an estimate of around 10 to the 18 seconds per cubic centimeter for this quantity. Now, what you can then do is you can try to estimate when this process should have started using these estimates. In other words, so we're not yet thinking about a hot Big Bang. In these papers, people were not thinking about a hot Big Bang, just a universe filled with a bunch of neutrons. And if it's only filled with nucleons at the time, it's matter dominated, and we can compute what the energy density is. It's just 1 over 6 pi g t squared. And you can then relate the energy density to the number density. As I just said, it's just rho over m. And in addition, you know that the neutrons decay, so you have an exponential decay here. And you can integrate this and try to estimate, well, you assume that it roughly takes of order the neutron lifetime, because otherwise it's just cut off. And then you can estimate what the initial time is, so when nucleosynthesis in a matter-dominated universe would start. And you find that it would start at a time of around 10 to the 4 seconds. Now, if you know the neutron lifetime, it's around 885 seconds. So the nucleosynthesis in a matter-dominated universe would start after all the neutrons have decayed. So you would find a universe that's filled all with hydrogen. So there wouldn't be anything but hydrogen. We know we don't live in this kind of universe, so this cannot be right. And one way out, as Alpher points out, and also Gamow, is a hot Big Bang in which the universe really was thermal. In this case, you have a bath of thermal radiation around. It dominates the energy density. The energy density in this radiation is much higher than the energy density in nucleons. The energy density in the nucleons we just estimated. The energy density in the black body radiation we can compute. It's the usual T to the 4 formula. It's much higher. It increases the expansion rate, and it makes nucleosynthesis start earlier. So this was the first hint. The problem with these estimates is really that there is a gap. So there are no stable nuclei with A equals 5 or 8. And this actually, for a while people thought, well, okay, this may be, but somehow you're still producing the heavy elements. But really they're not produced in this way because of the gap at A equals 8. And so Gamow also in 48, so there's 10 papers about all this in 48. So it's kind of interesting because you really see the development at this time. He provides an alternative estimate that's on the right track, as we now know, so it only relies on the formation of the light elements. And it's clear in this process, where you build them up continuously, starting from protons and capturing neutrons, that before you can form the heavy elements, you have to form deuterium. Now, for the formation of deuterium, you need the capture of the neutrons on hydrogen to be comparable to the Hubble rate at the time. And this is something, so Hubble at the time is just, here I'll just use it, Hubble is something like 1 over t, and you can come up with an estimate then for nt. So I'm just saying, you bring this over to the other side, you get nt, and n times t is just 1 over sigma v. Sigma v, so the capture cross-section for neutrons on protons is known, and the velocities at the time of when these things have energies of 1 MeV, you can also easily estimate. The capture cross-section is something like 4 times 10 to the minus 29. You can look it up in some tables. People certainly at the time also knew these kind of things because they were building nuclear bombs. So the velocity is 10 to the 9 seconds, and you find a density, or n times t, of 10 to the 20 seconds per cubic centimeter. And this, again, in a matter-dominated universe, gives you the same problem. So these are at least consistent with the estimates that you got based on this estimate that we now know is conceptually not quite right by Alpher and Herman. So again, the way out is to have a hot Big Bang, and this is also in the subsequent papers what is being studied. And they also, in those papers, already make an estimate of what the temperature of this radiation would be today. The estimate here is from the paper by Alpher and Herman, and the estimate is around 5 Kelvin at the time, which is remarkably good, even though these estimates were not, so the cosmology wasn't as well known at the time. So to some extent, it's a bit of a coincidence, but the order of magnitude at least comes out right. Now, let's look at it in a little bit more detail, how this actually works. And then, so if you're in a hot Big Bang, you know that there's a lot of photons around, and so they will actually destroy the deuterium that you're forming. So there's some formation, so you capture some of the neutrons by protons, but the deuterium gets broken up right away because of the radiation. And so nucleosynthesis in such a universe really takes place when the photodissociation of the deuteron becomes inefficient. Inefficient enough for the deuterons to capture additional neutrons in forming tritium and helium-3. The first careful study of this was done by Fermi and Turkevich. So here's the reaction for the light elements, all the reactions that they used at the same time. But this work was never published. I'm not completely sure why. If one reads around a little bit, it seems that it wasn't published because it was using cross-sections that from the Manhattan Project that were classified, and then by the time they were declassified, they weren't interested anymore, so they just told it to Gamow and Alpher, and they then summarized these works in their reviews. So another step forward, so at this time, everyone, for reasons I'm not completely sure about, was assuming that the universe was filled with only neutrons in the beginning, so 100% neutrons, and then protons only arise because of the neutrons decaying into protons. This changed around 1949. This was pointed out by Gamow and then shown in some detail in 1950 by Hayashi, that really the weak interactions are in thermal equilibrium. So at the time of interest, these reactions all happen rapidly. So you do maintain thermal equilibrium between the neutrons and the protons. And so one prediction in such a hot Big Bang universe you can make is the abundance of the light elements. And the way you would compute them is so you can compute the fraction of neutrons you have around. So on the one hand, you have the exponential factor that you just get from your thermal equilibrium calculation between neutrons and protons, and then you have the exponential decay, and you get a formula that looks something like this. This goes on until, as I said, the photodissociation becomes so inefficient that you can produce tritium or helium-3. This happens around 10 to the 9, and you can make an estimate based on our Friedmann equation when this is. This is around 3 minutes after the hot Big Bang. If you plug this in with the deuteron, the neutron lifetime, you get that the helium mass fraction is around 0.26. So this is a little bit too naive, and one has to do better, and one eventually finds 0.24. But this is a pretty good estimate, and this is one of the basic predictions in the context of the hot Big Bang model. So you had the prediction that the helium mass fraction was about 25%, and you had a prediction that there should be cosmic microwave background around to be observed, but this was forgotten for at least a decade. It's not completely clear to me why it is, but it seems to me that it is because it became clear that you cannot form the heavy elements in this way. So Alpher and Herman were always trying to explain all the elements in this way, not just the light elements. And it became clear due to works of Hoyle and many people that really the heavy elements really were much more likely to be formed in stars. So the irony in all it is that there was evidence for this radiation as early as 1941 in a paper by McKellar and others. So there's a number of papers on these cyanogen lines, and the estimate of the temperature from this was 2.3 Kelvin. There were also papers arguing that one couldn't explain this in standard ways. So, it's ironic because it's clear that Gamow actually knew about it, because the two guys talked about, I don't know what they talked about, but they did talk after a colloquium by Gamow. So this came back only around 1964, when Hoyle understood that nucleosynthesis in stars can explain the heavy elements, but it cannot really explain the amount of helium that's observed. So you can read this, I won't really read it to you, but this is the one line that started around a decade after all this stuff that led to the first modern BBN computations. And then around the same time, it's not fair to say it was picked up. In the beginning, the group wasn't aware of it, but Dickey in Princeton around 1964 started thinking about related questions. He was wondering if in a bouncing universe you could set up what they called a fireball, or a universe with hot and dense radiation that's left over and detectable today. And so he gave the theory question to Jim Peebles. He was asked to work out if you saw something, what you would learn, if you don't see anything, what you would learn. And the experiment was given to Roll and Wilkinson to work on. So this is the experiment, this is Wilkinson here, this is Roll that you can't really see behind the experiment. And 30 miles away, at the same time, there were Penzias and Wilson, and were troubled by noise in their experiment, and were trying to remove pigeons from the experiment, and tried to sort out various other things. They were wondering if what they're seeing is maybe some from the starfish atomic program, some nuclear detonations, but it turned out to just be the cosmic microwave background in any case. So they were informed by other people who had heard a talk by Jim Peebles, and then these papers you've probably all heard about or seen. So this led to the paper that claimed the measurement of excess antenna temperature by Penzias and Wilson, and the explanation of this excess antenna temperature in terms of the cosmic black body radiation by Dickey, Peebles, Roll, and Wilkinson. So as soon as you claim that it's cosmic black body radiation, obviously there's additional experiments you have to do, because so far you've only measured it at one frequency, and at the very least you have to confirm that it's a black body, so you have to measure it at multiple frequencies. And the first step ahead, of course, was the Princeton experiment itself, which was at a different wavelength, fortunately, from Penzias and Wilson. And then you had a data point here from Penzias and Wilson, and a data point here, and they were consistent with 3 Kelvin. But of course, you need to actually make sure that there is some, that you can also see the turnover, which took quite a while. And I won't go through that history, but I'll skip to the experiments that measured the black body spectrum the way we know it. So the first experiment is COBE. This is the experiment that everyone knows. Here's proposed in 1974. And here's the measurement in 1990. So it took about 15 years to do the measurement. And here you see the impressive measurement of the black body spectrum of the CMB. And this is still the best measurement of the black body spectrum of the CMB that we have today. Maybe over the next few years, well, there will certainly be proposals to remeasure it, and maybe over the next 5 years or so, we'll actually see another experiment that measures the black body spectrum. By now, the technology that exists today can measure this better at about 3 orders of magnitude better. And I'll say a few words about what the motivations for this are. Another experiment that I think deserves a lot more credit than it's received is an experiment that was done by the University of British Columbia. It was led by Herb Gosch. You can see that he was working on it for a long time. Here was essentially a failed experiment from 1973, where he's trying to measure the spectrum of the cosmic microwave background. And then around the time of COBE, they finally also succeeded. Just a few months after COBE, they had their own measurement of the black body spectrum of the cosmic microwave background. It's a an experiment that was called Cobra. He has Herb Gosch with what was left over after the flight. And the interesting thing to me is that it's really just a group of three people that led this experiment. So it was a competition between a humongous group, the Kobe satellite, and then the three people in Canada, which are largely forgotten because they were just a little bit too late in this, just a few months after the announcement, but I still think it's a remarkable achievement. It deserves more credit than it's received in the past. So now let me say a little bit from the theory point of view about the spectrum of the cosmic microwave background, a little bit about why it's black and maybe why it might not be quite black. So at early times, so first, how do we actually generate the black body spectrum? You need to have some processes that lead to thermal equilibrium. We know that in thermal equilibrium we get the black body spectrum, but what are the processes that actually lead to the thermal spectrum? There's Compton scattering, so you just have scattering of photons of electrons. You also have double Compton scattering, where there's an additional photon emitted. And then there's also Bremsstrahlung, so you just have electrons scattering off each other or electron scattering of protons and emitting a photon in the process. Now, Compton scattering is very efficient. While it's efficient, while it's fast compared to the expansion of the universe, it's very efficient in redistributing energies. The double Compton scattering, as you can see, can change the number of photons. These processes, both of them, grow at low frequencies, so you can change the number of photons at low frequencies and then redistribute them across the spectrum, and this is how you generate the thermal spectrum for the photons and generate the famous black body distribution. Now, at some point, we know that radiation no longer efficiently scatters off the matter, and the thermal equilibrium isn't maintained any longer. So you might ask why today we still expect it to be a black body spectrum. And to explain it, I'll work with an idealization where I first assume that all photons last scatter at the same time. We'll see that this isn't necessary, but let's start out that way. I'll also assume that we have a black body spectrum until the photons last scatter, which we'll see is a good approximation, but we'll have to justify why that is. And then I'll also ignore processes that inject additional photons for now. So, and those are the things that you can constrain if you make better measurements of the spectrum. So under this assumption, the only thing that's left, really, that can do anything is the expansion of the universe. So you might worry that the expansion of the universe distorts the spectrum. So this is certainly true that if you have a spectrum of massive particles, the expansion of the universe will distort it. But it's not true for massless particles, and it's easy to see. So you can try to see what's the spectrum of your radiation at some time t. So this is supposed to be after last scattering. And then what it is, it's just the original spectrum that you had at the time when the photons last scatter, but a photon that has a frequency new today at earlier times when it last scattered had a higher frequency. We saw this in our basic GR review. So the photons that are now frequency new at the time when they last scattered had a frequency that was larger than nu by this factor A of t divided by A of t sub L. And then also a frequency interval at today is related to the frequency interval at the time by this factor. And then you also just, from the expansion of the universe, dilute the number density of photons by one factor of the volume. So you have A of t sub L divided by A of t cubed. If you plug it all in, you see that this factor and this factor up here gives you the third power of A of t divided by A of t sub L. And this just cancels the volume dilution factor. And the only thing that remains is the factor of A divided by AL in the exponent here so the black body spectrum is preserved, but the temperature of the radiation redshift. So even though it's no longer thermal, it just is still a black body spectrum. So this is what happens after last scattering. It doesn't do anything. Here I'm assuming that it's instantaneous. You might ask, what happens if it's not instantaneous? Certainly nothing changes if at last scattering the energies don't change anymore. So this would also mean that the energy distribution of these particles is frozen in. To understand whether this is true, we should understand when last scattering actually occurs. And for these kind of things, you usually all want to estimate the rate at which they scatter off of the electrons and compare them to the Hubble rate. So they no longer scatter efficiently when you have less than one scattering event per Hubble time. So this is when the reaction freezes out. And let's first assume that there's no recombination and the number of electrons is just, well, it has to be the same as the number of protons to keep the universe neutral. And then you know the number of protons is the energy density in baryons divided by the mass of the proton. And then you have this redshift factor, A cubed. If you plug this into here, you find that this would happen at temperatures around 100 Kelvin, so very late. So they would scatter until very late, so this isn't quite right. We know that the universe becomes neutral before, so we cannot really assume this, and we have to understand how the universe recombines. In other words, last scattering, at least in our universe, is really triggered by recombination. So the question now is, when does recombination occur? And as a simple estimate, what you can do is you can estimate that it happens in thermal equilibrium. So all the processes are in thermal equilibrium, and then you can just use the formulas that you know from your basic classes on thermodynamics and derive this kind of a ratio. Here I'm assuming, or I'm dropping the differences in masses or energies between the 1s hydrogen and the protons everywhere except in the exponent, where B denotes the binding energy. And then here, this is the thermal de Broglie wavelength of the electrons. And the ones for the hydrogen and protons cancel. So you just get a formula that looks like this. If these don't look familiar to you, you should maybe just try to rederive these kind of formulas. Once you have this, you also know that the universe has to be neutral. So you can simply equate the number of electrons and the number of protons, at least after helium recombines. And if you introduce the free electron fraction, so the number of electrons per number of protons, you find an equation that looks like this. This is called the Saha equation, and here everything is known. This is the helium mass fraction that we already had a brief derivation in the earlier parts. This is the number density of baryons, which I wrote on the previous slide. This is the number density of baryons today and then redshifted. This is again the thermal de Broglie wavelength, so we know the mass of the electron, the temperature, we know the binding energy of hydrogen, and so we can just plot this as a function of temperature, and we find that recombination, if it were to occur in thermal equilibrium, happens around a temperature of 4,000 Kelvin. One slight subtlety is that recombination, at least for the low-lying states, doesn't really occur in equilibrium, but there's one has to be a little bit more careful in the derivation. We'll see it doesn't modify it too much at this qualitative level that we're discussing it, but in detail it's actually important. So let me briefly just tell you why this is and what the equation is, but I won't derive it because it takes too long. So it doesn't really happen in equilibrium because, on the one hand, if you have electrons and protons combine and fall into low-lying states, the photons that are emitted ionize atoms in other places. So there was no net decrease in the ionization. Similarly, if you have photons that are emitted from transitions from highly excited states to low-lying states, they excite other atoms, and you have no net change in the excitation levels. And the Lyman alpha photons that you get from the transition from 2p to 1s also are very efficient in exciting other atoms from 2p to 1s. And this means that, there's to some extent the expansion of the universe helps. This will eventually kill it, but it makes it rather inefficient, so that you, for example, have to consider this the forbidden 2s to 1s transition. These kind of things were all worked out first, I mean, by Peebles and independently by Seldovich, Kurt, and Sunyaev in 1968. There's some differential equation one can write. I won't tell you what all the ingredients are, but these are functions of time. This is, again, some difference in energy levels. And then if you include this departure and you integrate it, you find that it's a little bit delayed. So it looks, in practice, looks like recombination looks like this, but happens at a similar temperatures to what we had before.
So roughly about 5 minutes.
Okay, I'll hurry up a little then. Okay, so what you can do once you have the density of the free electrons, you can compute the probability for the photon to last scatter at temperatures between T and T plus dt. And here I'm showing you the probability distribution. And you see that photons typically last scatter, or this peaks at an energy, at a temperature of around 3000 Kelvin. And so the question was, if energy is still exchanged efficiently, then for this you have to do a similar estimate to the ones we did to understand how long they scatter efficiently. And you find that energy is only exchanged efficiently at temperatures above 10 to the 5 Kelvin. So here, again, you just have to plug in the various things, the Thomson cross-section, the Hubble rate, etc., and you can work it out and find that this happens at around 10 to the 5 Kelvin. And so Thomson scattering doesn't modify the spectrum at temperatures below 10 to the 5 Kelvin, in particular doesn't modify it at a temperature of 3000 Kelvin. So even if last scattering is extended, it will not modify the spectrum. So the next, if you have an injection, as we said, we were ignoring them, but there are processes that actually do inject photons. So it means that if you do inject photons at that time, which you do during recombination, then this does lead to distortions. And here, this is a paper by Jens and Yassin, and you see the recombination, the distortion from the recombination lines. You should remember the scale here. I'll show it again later, but so this is 10 to the minus 26 in these units, so we'll see quite small. Above 10 to the 5, energy is exchanged efficiently, but the question is when you want to keep the black body, until when you can also produce the photons. Double Compton scattering freezes out at a temperature around 6 times 10 to the 6, so the eras you have is until, or at energies above, or temperatures above 6 times 10 to the 6 Kelvin, you very rapidly establish a black body if you inject energy there. Temperatures between 10 to the 5 and 6 times 10 to the 6, you have what people often refer to as the mu era, because you can no longer create photons efficiently, but you can still redistribute the energy. So you get a Bose-Einstein distribution in this era if you inject something. And then after this is often called the Y era. So you no longer redistribute the energies. And so here are some of the potential spectral distortions. These are the recombination lines that I showed you on the previous slide. There's other things that I haven't yet had a chance to talk about. So there's silk damping, which we'll hear more about. And then in principle, there could be more spectacular things like decaying particles. But again, remember the scale. So the absolute black body spectrum looks like this, and I'm intentionally drawing it at the 10 to the minus 23. I'm stopping. So all the distortions are way below this. The interesting, remarkable thing is that we might still be able to detect these tiny distortions with future experiments like PIXI or PRISM. And since I'm out of time, I'll just end it here, and then we'll...
Okay, so we have time for a few questions, if anyone has any now. We have a microphone if you want to ask.
You mentioned that Kobe measured the blackbody radiation more precisely. Why isn't Planck or WMAP? They do measure spectrum in few frequencies, right?
Yes, but not anywhere. So these are not, they weren't absolute measurements. So the spectrum, as you saw from Kobe, you have really many data points. For Planck, you only really have 9 data points, and they're not absolute measurements. So they're calibrated in other ways relative to the dipole, which I haven't yet talked about. So they're not really precise enough to be better than Kobe. So Kobe, this is the measurement not by Kobe DMR, but by Kobe FIRAS, which really measured it relative to a reference black body that was on board the spacecraft, which is not something that Planck did. So these future experiments, Pixie would be the same as, well, it's Kobe, but with newer ingredients, and Prism would be an even more, well, I don't know. These experiments also, one should say, so Pixie would be reproposed sometime next year, so this might happen soon. The Prism, I mean, all the CMB experiments in Europe look like they will be happening maybe in 20 years from now. But in any case, so the difference really is that they measure the spectrum in an absolute way with a reference black body, while Planck does not, and WMAP.
What kind of new physics do you need in the small distortions that you observe?
You just say it again with the mic.
What kind of new things do you expect to discover or to find looking at the small distortions for the...
So one of the things I was showing you on this slide that people included here, for example, are decaying particles. Now this is a little bit limited because, as I showed you, it's only a very small range of temperatures between today and the 10 to the 6 Kelvin that you have to inject the energy from these decaying particles. But in principle, if you have particles that decay during that period, it would show up as a spectral distortion of the cosmic microwave background, so you can put constraints on these kind of things. You can also, an interesting thing is the silk damping, which I haven't said anything about yet, but it's due to diffusion of the photons on small scales. They transfer energy or inject energy into the CMB on large scales, and this, for example, gives you a measurement. It's an integrated measurement, but it's still a measurement of the amount of power that you have on these small scales, which you cannot measure otherwise because they're suppressed because of silk damping. And so if there were any strong running in the primordial power spectrum, or if there was something strange going on in the primordial power spectrum, you could, for example, detect something like this.
So I want to ask, for Pixie and Prism, are they going to be able to measure anisotropy as well?
Yes. So
much
both
better
of
than
them.
Planck?
Yes. So Pixie would have somewhat lower resolution. It has much higher frequency coverage. I mean, it has something. I mean, it's a Fourier transform spectrometer, so it's a very different experiment in practice. But it roughly has 400 frequency channels, so you can do much better with the foregrounds, for example. But it has lower. This one, the proposal for Pixie, has lower angular resolution. For Prism, it's it's a very ambitious experiment, so it would do everything better than everyone has done before. So it would do the spectral distortions much better than has been done before, and it would also do the anisotropy measurements much better than anyone has done before.
Also, I have another question. Of all those dips, I don't quite understand why there's a...
Yeah, I didn't really explain, but these are... I didn't have time to derive, but one of them is positive, the other one is negative, so there's really a sign change. So it's just plotting the absolute value, because it's a log plot, but it's really a curve like that.
May you also comment on reionization and structure formation in this plot? Because it seems
Yeah, so it's also, yeah, I mean, just if you inject new photons from stars, you would also see it in principle. In practice, I'm not actually sure how one can disentangle all these different effects and how much you learn about what's coming from what. But I think Yassine might know more about this. I know Jens has been trying to work on it. There's some principal component analysis now where in principle you can take out the different templates and try to learn what's coming from where, but I haven't actually worked on trying to disentangle the various distortions. So mu distortion is relatively clean. A lot of things lead to Y distortion, so it's not so clear how you learn something from it. But I mean, Jens's last talk I saw at least was optimistic. So, but in principle, this is just photons that are injected and that you would see and that just distort the black body.
Which one would be the largest signal you would expect?
Well, I mean, this is the plot. So these are the various signals, and this is their
top
strength.
One, the
so and these are
realization.
Y distortions. Yeah.
Okay, so we're going to have more time for discussion. The last hour of the day is going to be making up questions and interrogating the speaker. So if you have other questions that come to your mind, please say them for the afternoon, and we'll have fun with that. So before we move to the next speaker, let's thank Raphael again for a great talk.